G'day again, guys. So we're continuing on in topic 1, in particular that 1.5 that, as I said, we would break down into some smaller sections. So in particular 1.5, looking at the circulatory system today. Now, circulatory, as the name suggests there, circulate, all right? Circular, in other words, going round and round. Circles around, going round and round, circulate, move it around. So the main role of the circulatory system is, as it says right there on that first slide, transport blood. So when it comes to us as exercise physiologists, what we want to focus on blood is getting blood around the body, because blood carries oxygen. So that's the big thing for us. So the more blood we can pump around, the more oxygen we can pump around. So how much blood's actually in the body? Well, men generally have a little bit more. Why? Just because they're bigger. Okay. Now that starts to make a little bit of sense when you start looking at all the Olympic records, whether it be jumping, throwing, running, swimming, whatever it might be. The male record will be faster or further or whatever it might be. Generally, blokes have more blood, therefore they're able to carry more oxygen. Able to carry more oxygen, what does that mean? They can work at a higher intensity for longer because they're actually getting more oxygen to the working muscles. So if we looked at it, 1500 metre runner, since the men have more blood, they are carrying more oxygen, which means they can work at that higher intensity for longer. Blood is broken into two sections: solid section, which is generally the blood, and then a liquid section, roughly about 50-50. Okay. Bit of information on red blood cells, or RBCs. Now, you might go, Mr. Driver, how much of this do we have to actually know for an exam? Well, you're probably not going to be asked what's the life cycle of a red blood cell. No, but it's just worth knowing a little bit. Okay. Main thing we need to be aware of is this last point: contains hemoglobin. Now, as we've spoken about previously in different slides and lectures, heme meaning blood. All right, it contains hemoglobin. All right. So, which transports oxygen from the lungs around the body. So in other words, the hemoglobin, that actually grabs onto the oxygen, if you like, and carries it around the bloodstream. White blood cells. Okay, if we just have a look here at the few produced in bone marrow and lymph tissue, move to areas of infection. So they're there for fighting off infection. That's their main job. Okay, then we've got platelets, responsible for the clotting of the blood. Now there are some diseases like haemophiliac where people can't actually, their blood can't clot, so they might get a small little paper cut, and since the blood doesn't clot, right, it can continue to bleed. Whereas people that don't suffer from it, they get a paper cut, hold a tissue over it, it'll generally hold the blood up and it will dry up. Okay, and plasma, all right, contains water, which is absorbed into the bloodstreams, and nutrients, which are transported around the body. So I said there's a bit of detail there. How much of that do we need to know, driver? Probably not a great deal. Be aware of that information, understand it, but we don't need to remember a heap of it. Arteries and veins. Okay. Arteries and veins, their jobs is to carry blood away from the heart or towards the heart. All right. Now, arteries, A for away. Okay. As the first point says, carry blood away from the heart. So, blood is pushed through the arteries by surges. In other words, each time your heart beats, it forces the blood along. Okay? Imagine the water in a hose. Every time you breathe down the hose, it forces the water along. Very similar sort of concept, except instead of blowing on the hose, it's your heart pumping. Instead of water in the hose, it's the blood in the arteries. The artery walls are elastic, and they'll expand. So in other words, that hose, as a big surge of water goes through, the hose will extend a little bit, all right, or expand, and then as the blood moves through, it'll go back to its normal size. Pressure decreases as blood gets further away from the heart. So does speed of flow. That makes sense. Right? If we think the heart is the actual pump, the closer we are, the stronger it's going to be. But as we get right out to our toes, right, that pulse isn't going to be as strong just because it is further away. So arteries, their job is to carry blood away. So capillaries, they are fed by arterioles, and they're tiny, thin. okay? Very thin, semi-permeable. Now, permeable means water can transfer through it. Semi-permeable means, hey, it can in some parts. So, it allows oxygen and carbon dioxide to pass through. So where would oxygen and carbon dioxide swap over? We start thinking, hey, that's going to happen somewhere around the lungs, because we want to breathe in oxygen, but we want to breathe out carbon dioxide. So that diffusion can actually happen at this point. Veins. Their job is to take the blood back towards the heart. Now, pressure of heartbeat is too low to push blood back. So what they'll actually do is, if you like, they've got valves. So imagine that water's in the hose. If I squeeze the hose with my hands, it's going to force the water up. So if I squeeze it with one hand, it forces the water up. I then squeeze it again, it goes up again. Keep squeezing it the whole way up. And it's a similar concept with our veins. However, instead of putting my hands further and further up the hose, okay, it's actually the muscles. So the muscles contract, meaning they get bigger, they squeeze the veins and they force the blood up. And that continues the whole way back till blood comes back to the heart. Okay, so this is the heart we're looking at. Two top sections, atrium, and our two bottom sections are ventricles. And it would appear as it's in the heart. So if I look at that image and go, okay, I turn myself around so that that heart is lined up with mine, the right atrium, all right, is on the right side as it would be in the body. And then we've got the right ventricle. Remember, alphabetical order. A becomes before V, so A is on top. Then we've got the right ventricle. Then we've got the left atrium and the left ventricle. Okay, so if I just try and be a little bit clever and go with some sort of colour here, like we go with green. So blood's going to come back in to the heart, comes into here, and it will come into this right atrium first. Then it's forced into the right ventricle. Now that's coming back from the working muscles. So it's coming back in this way. That's an arrow in case you can't understand that. Right? So it's come back in from the working muscles. So if it's come back in from the working muscles, it is going to be, all right, lacking in oxygen. All right? In other words, it's going to be rich in CO2. So what happens here is this gets pumped out through here and it will go out to the lungs, where that diffusion of carbon dioxide and oxygen swap over. So in other words, our body gets this rich oxygen stuff back in, comes back in through here, into the left atrium, then into the left ventricle, and then it's finally pumped out the bottle. The top. Okay? So if I go forward and back just to clear my sheet there. Right? So in other words, we go through that again. CO2 rich comes in, goes out this way, gets pumped out towards the lungs. We swap it over for rich in oxygen, comes back in through this way, and then finally out the aorta. Okay? And the process can continue. So, the heart, how it works. When it contracts, squeezes blood out of the heart into the artery. So think it as like a sponge full of water. And when you squeeze the sponge, the water goes out. Same thing. Right? So, when the heart relaxes, it fills with blood. So you think of the sponge. When you let the sponge go and put it in water, it soaks it up. As you squeeze it, all the blood goes out of it. Okay? So the process when, if you like, we squeeze the heart and the blood goes out is called systole. And when we relax it and it fills, diastole. And you might have heard on TV shows or where they talk about blood pressure. All right? These are the values they're talking about. So, heart rate, HR, commonly known as, measured in beats per minute. Now you can easily just take your pulse rate or connect up to a heart rate monitor to find out. Your heart rate is a very interesting thing. It can be increased by fear, excitement, exercise, eating, smoking, taking drugs, temperature changes. So all those things can increase our heart rate. Exercise is probably the one we focus most on. Where we begin to exercise, our body says, hey, we need more oxygen. So as a result of needing more oxygen, your heart beats faster. Why? Because what's in blood? Hemoglobin carries oxygen. Right? So as soon as we start to exercise, our heart will beat faster to circulate more blood. This one here, taking of drugs. What synthetic drugs like your ecstasies, your crystal meths and all that will actually do is they will force the heart to beat at an unnatural pace. Now, how do we calculate our maximum heart rate? Hopefully you've said 220 minus your age. So if we pick on most of you guys being, let's say, 18, your max heart rate's going to be 202, theoretically. Now, you can go a little bit over that. It's not the end of the world. But what some of these artificial drugs will do is they'll force your heart to actually beat at a faster rate. Okay? Something your heart is not actually supposed to do. And this is why we can actually see people suffer overdoses, because their heart is forced to beat at an unnatural rate. Their heart goes, dude, what are you honestly doing to me? I can't keep this up. So your heart goes, I don't want to keep this up. It stops. Okay? So no amount of drinking water is going to help you with that, which is why these can be potentially very dangerous substances. Okay? Heart rate increases the demand for oxygen we just spoke about. Why? Because as soon as we exercise, hey, I need more oxygen, right, we've got to pump more blood because blood carries it. Right? We spoke about our max heart rate, 220 minus your age. So as we get older, our max heart rate will drop, which is why it is harder for us to perform things that we could do as an 18-year-old when we get to 30 or 40. We think, I can still do everything I could do then. Well, no, all right, your max heart rate's actually dropped. At an 18-year-old, your max heart rate's, in theory, about 200. As a 40-year-old, your max heart rate's 180. So it is going to be a lot harder. Average resting heart rate's about 65, okay. In theory, the lower your resting heart rate, the fitter you are. Why do you think that is the case? Because you're sitting there doing not much, your body's saying, I need, whatever it be, X amount of oxygen. Your body is saying, righto, I can get that by only beating 15 times a minute. Whereas if you're unfit, your body's going to go, well, hang on, I'm going to have to beat my heart probably about 40 times a minute to get that. So we use, generally as a rule of thumb, the lower the resting heart rate, the fitter the athlete is, or the person is. So, heart rate equations. These are terms that you'll need to know inside out, back to front, and these are terms that definitely come up in exams. Right? So make sure you know these. Your little definition book that we've spoken about previously, right, you might want to write these down. If you've got them to the point where you've got them under control, fine, rip them out. Stroke volume is the volume of blood in litres ejected in the aorta per beat. So in other words, stroke volume is how much blood the heart can pump out per beat. That's what we're looking at. Approximately about 70 mils, can be up to 90 or 100 mils. Heart rate, number of times your heart beats per minute. Cardiac output, which is quite often referred to as Q, the amount of blood pumped out of the heart in 1 minute. So in other words, this is saying how much blood is pumped out each beat. This is saying how many times it beats per minute. We put the two together and we can find out cardiac output, which is why the equation is cardiac output equals stroke volume times heart rate. Okay. So blood pressure we spoke about previously, where we've got systole and diastole. Okay. And you'll quite often hear it referred to as 120 over 80. Right. So in other words, when we use the example of the sponge, when the sponge contracts and relaxes, or the sponge absorbs the water and squeezed out, they're the two values that go into our blood pressure. Okay? Again, factors that impact on blood pressure. Arteriovenous difference is a term you may have heard of, and if you haven't, it's okay. Let's break it down. Arteriovenous difference. Arterio, what does that sound like or look like? Sounds like, looks like arteries. Venus, not the planet, all right? Venous, veins. So we've got arteries, veins, and the difference, which is quite simply what it is. The difference between oxygen levels in the blood of arteries and that of the veins. So we spoke about, all right, arteries take blood away from the heart, veins bring it back. So, you imagine you're going for a jog around the oval. Blood is pumped out of your heart. It's going to be rich in oxygen. It goes down to the working muscles in the leg. What are those working muscles going to do? They're going to go, hang on, we need that oxygen. So they take the oxygen out of the blood. They use it for the working muscles. And then they send this blood back that's poor in oxygen, rich in CO2. So what we're looking at is going, okay, what's the difference between the amount of oxygen in the blood in the arteries on the way down and the amount of oxygen in the veins on the way back? And that is termed arteriovenous difference, written as A take VO2 diff. Okay. A few questions there that if you want to pause the screen, have a look at them, give them a bash, and as always we can speak about them in class. Otherwise we'll keep moving on. Acute responses to exercise. Acute is what? Acute means short term. So in other words, what are short term or immediate responses to exercise? So in other words, I go from sitting on my ass to running around the oval. What are going to be some changes in my body? That should be heart rate, sorry. Heart rate increases, which is the number of times it beats per minute. Stroke volume is the amount of blood pumped out per beat, increases. Cardiac output increases. Well, that makes sense because these two times together make this. So if this has gone up, this has gone up, cardiac output goes up. Arteriovenous difference increases. That means the working muscles are taking more oxygen out. Blood flow increases. Oxygen uptake increases. You can see they all increase. And we think, why? Well, quite simply, I need to get my heart rate up, so I'm pumping more blood. I need to get my breathing rate up, so I'm breathing in more oxygen. All responses to exercise are about getting more oxygen to the working muscles. So my body responds in that way, pumping more blood around, getting more oxygen in. If I get more oxygen in and I pump more blood around, my body is going to be happy. Heart rate, we've pretty well spoken about this before. Heart rate will increase because our body needs more blood, because blood carries oxygen. Max heart rate, 220 minus your age, is definitely something you're going to need to know, and you'll refer to a lot. Whenever you get a question or a graph, have a look to see, does it have the age of the athlete, because that will give you a fair indication as to what percentage of their heart rate they're working at. A 20-year-old with a heart rate of 160 beats per minute isn't working that hard, because 160 out of 200, right? Whereas a 40-year-old working at 160 beats per minute has a max heart rate of 180, and suddenly they're getting very close to their max. So age does play a big role. Stroke volume. Again, we've spoken about the volume of blood pumped out of the heart per beat. Resting values 70, approximate max values of 90, some even up to 100. Okay. As we begin exercising, stroke volume is going to increase. Why? We want to pump more blood out. Pump more blood, carry more oxygen. Cardiac output. Okay, we've spoken about that. Volume of blood pumped around the body per minute. That's how it's calculated, and it's in litres per minute. So for example, stroke volume, 90 mils, heart rate, 170 beats per minute. Put the two together, we get this answer. However, 15,300 mils per minute, it's in mils. We'd prefer it to be in litres. So what do? Divide by 1,000, and now we've got ourselves a good value. All right, so that's another little trick where they can catch you out just based on the units they're using. A take VO2 diff, difference in the arteries and veins and oxygen. Okay, so let's say there's 20 mils of oxygen per 100 mils of blood in the arteries. The working muscles rip some out before it comes back. 14, the difference is 6. Okay, max 20 mils of oxygen per 100 mils of blood in the arteries, 8 mils of oxygen per 100 mils in the veins. Okay, suddenly 12. Why the difference? So in other words, we've gone from that same 20 value, but here there was 14 mils of oxygen going back to the heart, whereas here there's only 8 mils of oxygen going back. Why is there more that's been taken out? Why would the working muscles take out more oxygen before it returns to the heart? And if you said because you're working harder, then you're spot on. Right? More oxygen is going to be removed because you are working harder. Blood flow. Your body is very clever. it redirects blood away from non-essential areas. So in other words, when we're exercising, there's not going to be a lot of blood flow to the kidneys and liver because while we're exercising, we don't need them. Right? Same as if our body's put into survival mode. Right? Let's say we're out somewhere cold. It's going to restrict the blood flow out to the limbs. It's going to keep it around the vital organs. Right? But while we're exercising, we're not in survival mode, so our body will go, hang on, let's keep it away from this stuff. Right? And let's put it towards the working muscles. So that's another one done. Thanks, team. We'll catch you next time.